So today we're going to talk about biopolymers, the natural fibers, and the biological systems produce some amazing structures. I mean, you're familiar with DNA, the double helix. You're also probably been amazed if you've had biochemistry at the wide variety of enzymes and polymers that use all of the different amino acids. Well, today we're going to focus a lot on saccharides, so all of the different sugars and starches and how we store energy in our body. All of these fibers are biopolymers as well. And then we'll take a few cahoots just to kind of review some of the gunshot, residue, and arson stuff that you were covered with the external lecturers. So we'll talk about the terminology of polymers, because we're going to do biopolymers today, and then next time we're going to do synthetic polymers. And you'll be surprised. You think that we would have more, that we could produce more complex fibers with all of our scientific expertise, but actually we cannot compete with living organisms in terms of the complexity of the polymers. Now we're pretty good now with our mechanics. We can make proteins and so on. We can synthesize, but it's not nearly as efficient. And so that's why you have the whole field of natural product synthesis. A lot of times we'll use organisms to produce really complex proteins. We could produce those in the lab, but it would be very difficult. And then we might not be able, even possible for us to synthesize a properly folded protein. And so with the function of the ribosomes and so on in the body, there's not just the primary structure, but also secondary and tertiary structures of the folded protein that make them active that we have no way to reproduce externally. And then we'll get into today biopolymers with natural rubber, polysaccharides, and proteins. And then we'll talk about how we work with natural fibers, like cellulosic fibers, making threads for our clothing. And so those are going to be some of the fibers that you find in a crime situation, and then protein fibers in the form of hair. So this is a subset of all of polymers. We have biopolymers, and then we have in this middle semisynthetic polymers. We'll discuss what that means. And then next time we'll talk about all of the synthetic organic polymers and different ways of making them with addition reactions or condensation reactions, ring opening or free radical polymerization, and some other techniques. So let's talk about the polymer basics. So how many people have heard of PVC? Okay, that stands for polyvinyl chloride, and this is the monomer. So mono meaning one, so this is the single unit that's polymerized to make polyvinyl chloride. This is vinyl chloride here. And so the vinyl is another word for this unsaturated carbon-carbon bond, this double bond. And that is a very active group. And we can use anything with a double bond. This is your take-home lesson, one of the take-home lessons. Anything with a double bond can be polymerized. In fact, on the MSDS sheet, one of the categories of hazards that you might find on a safety data sheet is the risk of violent polymerization or exothermic polymerization. Because if you think about it, if you put acetone in acetylene in a tank, acetylene has a triple bond. You try to pressurize that tank with acetylene, and you have gas in close proximity, and you have all of the triple bonds, it can polymerize, and that's an exothermic reaction. And so this is a very unstable situation to pressurize acetylene in a high-pressure container, because it can blow itself up once it starts that polymerization reaction. So what we do to stabilize acetylene, I mean, if you've ever been around a welder, he uses an oxygen acetylene cutting torch. And you've got a cylinder of acetylene in there. And that cylinder will say, please keep upright. Doesn't matter if the oxygen cylinder is upright, but the acetylene cylinder has to be upright, because inside that cylinder is also a bunch of acetone. And so to keep the acetylene from polymerizing violently, they put acetone in that tank, and then they pressurize the acetylene or dissolve it into acetone. And so it has a vapor pressure that's mostly acetylene, and so you're just using the vapor pressure in your cutting torch. But it's stabilized with acetone. Kind of like we have the explosives. We wet the explosives to keep them from reacting violently. This is a very similar effect. So anything with a double bond can be polymerized. Now there's different types of polymerizations. You have the random polymerization, and let's say you have two different types of monomers. Or if you wanted to, let's say you had some vinyl chloride and it was mixed in with say, vinyl fluoride. So it's really not that much different in terms of the monomer. You just have a fluorine instead of a chlorine. But because you have two different types of monomers, you might have a random polymerization, X, Y, and then 3 Ys, and then a couple of X's, and then a Y and an X. And this is what would happen in a beaker. You know, you put these two together, you start the polymerization reaction. You know, it's statistics. You're just going to have a random collection of monomer units coming in, and some will be fluorinated, some will be chlorinated. Okay. And that's what you would definitely get if you had vinyl chloride and you were just using, say, a free radical polymerization. Once you make a radical on that carbon, then it can just attack those double bonds, and the first double bond it sees, it's going to attack. Other XY type polymerization might be block polymerization. So in this case, you might take a polymer of form X and build up a very short chain polymer with X in beaker 1, and then a short chain polymer of Y in beaker 2, and then mix those together and link the chains together. So there might be reasons for doing this. You might have X be a little bit more rigid than Y. And so you have a strong rigid component to the polymer, and then you have a really flexible component. And so you build the flexible component, you build the rigid component, then you put them together and link them together. And this is one of the polyurethanes that I was familiar with at Pantex. It was called Estane. And it had a rigid component that had 4 to 6 units. So there'd be like 4 or 6 to 6 X's, and the reason it's a range is because it's just chemistry in a beaker, right, or in a reactor vessel. And so you can't control that it's exactly 5. You can aim for 5 and you get 4 to 6. Okay? And then you take that pot out, and then you make a long chain that has like 6 to 10 flexible units, or maybe even up to 15, and that provides the ability of the polymer to squish and make elastic properties, and then you mix the soft and the hard chains together, and you make a polymer that has soft domains and hard domains. And that is a polymer that's rigid enough to hold its shape, but flexible enough to not break when it gets hit. If it's too rigid, it'll break. Okay. If it's too flexible, it won't hold its shape. And so we can fine-tune the polymer properties by using block polymerization. We can make something that's just the right hardness and shape memory that we want. Now, some polymers by nature have to be alternating polymers, and nylon is one of those. So this one is nylon 6,6. So it's got this diaminohexane group, and then this right here. This is 6, even though it shows a 4 right there, and there's 2 carboxylic acids. So that's a diacid, saturated diacid. And there's a lot of those. You can tune the properties of this nylon by picking a different diacid. Did y'all learn in organic chemistry your diacids, the names? Do you remember the mnemonic, oh my, such good apple pie, sweet as sugar? So, oh my, isoxalic, maleic, so my, such succinic, such sweet, apple pie. Adipic is apple. And I know that's the 6th one. And so this is adipic acid mixed with diaminohexane. And so you pick adipic acid, you have nylon 6,6. Okay. Glutaric, you have nylon 6,4 or something like that. And again, you can tune those properties of that polymer by picking a different diacid and a different diamine. So, but that by nature, if you notice, it's an amine group reacting with an acid group to form this bond in the middle. So this is an amide bond. And what we've lost is water. So this is a condensation reaction. And this polymer nylon is alternating. It has to be. You have an amine, acid, amine, acid, amine, acid. So it's XY, 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 all the way down. And then you can have graft polymerization, where you have a polymer that's all X, and then you graft in Y. So you have some branching. Branching also produces softness in a polymer, okay, because you can't pack it as tightly. You can pack linear polymers pretty tightly. That's where high-density polyethylene is, HDPE or HDPP. So polypropylene, that's your milk jug polymers. You think about how much polymer is in there. You could, just take a very dry, empty milk jug and weigh it. It's not very heavy. That means there's not a lot of polymer there. Okay? And yet it holds 8 pounds of milk. It's a pretty strong container if you think about it. There's very little polymer involved. Some of our polymer-bound explosives that we had, this was a structural plastic. It was as hard as this plastic that we make our rigid products out of. It was machinable, but it only had 5% polymer. Mostly it was explosive, so it was only 5% polymer holding that thing together. So that was the glue that held together that structural object. You can also have endimers. A lot of times these will start with a nitrogen, and then you polymerize out from that nitrogen, and it makes this fluffy ball because of the branching. Also something that you can't pack very densely at all. Let's talk about these cross-links. Cross-linking is one of the most important properties of polymers. It can dramatically change the behavior of a polymer, and that's one of the things that we do when we perm a hair. If you take your hair and you get it permed, they put a reducing agent on it, and it takes all of those sulfur disulfide bonds that you have in your hair proteins. Your hair is a protein polymer, and it breaks those disulfide bonds and allows it to be straightened out. You roll it up on curlers, okay, and then you oxidize it again, and then it goes back to the forms of disulfide bonds, but now they're all linked into a curly shape. You pull the curlers out, and the hair retains that shape. So we're actually doing chemical reactions on the protein when putting a perm in. Okay. Now, I guess you could do the same thing, but with straightening. It wouldn't be a permanent curl, but I guess you could do sort of the same chemical process, but hold your hair straight and then get it chemically straightened. I don't know if they do that or not, but chemically it seems like that would work. Anybody heard of anything like that, or is it permanent? You can't. Is that what it is? Relax. Okay, I didn't know what the term was, so I don't have any. But we've learned the chemistry of our polymeric hair, and it's an amazing amount of chemistry in personal care products. But this cross-linking is pretty dramatic, and that's the difference in these two little rubber balls. So let's go to, let's see, let me pick this up and go 5. Okay, so let's go to right here. So the difference between these two balls is one bounces pretty well, like here it is back. Okay, and this one, isn't that strange? And what's the difference is, this you can kind of see, one's a little more shiny than the other. Okay, this one's a little more shiny. And that's the one that bounces. Okay? And at first, when I first bought these, they were both, I couldn't tell the difference. But now one's a little more shiny. So what's going on with these polymers is the same material, but one's a little more cross-linked than the other. Okay? What does cross-linking do in a polymer, if you think about it? It does what? It packs it, and it doesn't change the density. Okay? So these would be the same density. Yeah, distribute. Let's think about the permanent. Okay, I'll pull on that hair, I've deformed it. What does it do? It springs back, doesn't it? So it's shape memory that we're talking about. So it's really energy storage. So a distribution is the non-cross-linked polymer that loses the energy. It's distributed along the fibers and it can't come back. But with the cross-linking, we have a chemical bond that holds those polymers in place. So it does try to be distributed from fiber to fiber, and then that cross-link pulls it back. And so it's what we call energy storage. And now we're not really storing energy like recoverable energy in the sense of like power, like for batteries and so on. But it's energy storage in terms of insult. So when I drop this one, this is the cross-linked one, and I drop it, and it's compressed, and then it decompresses. So it's like pulling on the strand. It's like a spring. That cross-link makes this more springy, and it returns the energy that it had. So here it lost its vertical energy, compressed the polymer. The cross-links push back, push the point back in the shade, and return that energy back in terms of velocity. Whereas this one is not cross-linked, and all that energy goes into random vibrations in the polymer. I just wanted to show you an example of the use of cross-linking in shape memory. This one has a lot of shape memory, the cross-linked one. And so it wants to stay spherical. If you squish it, it pops back. This one is not cross-linked, and it loses that shape memory. It gets squished, and then it goes into random. So this one's a little warmer now. I've been dropping it. I can't feel that, but I know, this one should be more warm because that energy has been distributed throughout those polymers, and they've slipped past each other. So let's talk about shape memory. And let's, I guess, start at really low temperature. If we cooled those polymers down, they would eventually become what we call a glass. If they have the ability to slide past each other, they could even form a crystalline phase where you have a nice pattern in the molecules. Okay? It won't be a single crystal just because there's too much randomness in how the chains are all pulled together, but you might have crystalline domains, really rigid crystalline domains. And so that's what you have at really cold temperatures. If you start to warm it up, you have this glass transition temperature. And that's where the polymer, you've activated certain vibrations in the polymer. And now the polymers can move past each other. They don't melt, though, but they're more flexible. And so that's when the polymer goes from being inflexible to flexible. So we would experience this if we had liquid nitrogen and we put a rubber tube, a flexible tubing in there. It would go below its glass transition temperature and be very rigid. And you can break it just like glass. It sounds just like glass. It vibrates just like glass and shakes the air. And so at below the glass transition temperature, your polymers are very susceptible to damage. They'll crack, they'll break. They're just like glass. You get above that glass transition temperature, and the polymer still has shape memory. So it still maintains its shape. And if you push on it, it springs back. Okay. But if you keep warming it up, eventually you push on it and it doesn't come back. And that'd be a gum. And then you get above that, you get to a sticky gum, where it actually parts of it start to come off. And then you get to a melt. Okay. Now some have a sharp melting point, and some do not. Some go gradually from a gum into a liquid, and it's just a tacky, sticky mess. Kind of like the asphalt on the street, and sometimes in August you're walking along and it's starting to get tacky and gummy and it sticks to things. But there wasn't really a melting point. It wasn't like a sharp temperature at which the road melts and then the rocks start sliding off the top. Yeah. So one of the most common polymers that we have is from tree sap, natural rubber, and remember we had for the poppies, they would scratch the poppy seed pod, and the natural liquid that came out they called latex. So any kind of plant sap is latex. That's a generic term for latex. So when we talk about latex gloves, it's natural rubber. Okay. And so this is, you take that out, you have this monomer called isoprene. It's like a 5-carbon molecule with a couple of double bonds. And again, it has a double bond, it's unsaturated, so it can be polymerized. So we just take this tree sap, we dry it a little bit, get rid of some of the water, and then start reacting it, and we can make rubber. There's different ways to react it. You can make a cation, you can make anions, you can do free radical polymerization, and we'll talk about those things on Thursday. Okay. But the point is, you see those double bonds, you say, aha, that's a possible polymerization. Now, I talked about adding in hard domains to make something tough, to make it hold its shape and actually give it abrasion resistance. And so we'll take natural rubber, we'll start to polymerize it a little bit, so we'll make a small sort of viscous fluid, and we'll fold in a lot of carbon black, like charcoal, and fill that with charcoal, and then start the polymerization again and make like a thick black called butyl rubber. And that's what these boots are made out of. You can see that they've been pressed into a form and they haven't cut off the extra amounts. But your mudding boots are made out of natural rubber. It's tree sap mixed with carbon black and then processed into shape. And it's it's very water resistant because it's just an organic molecular polymer. Now, how do we get those boots to hold their shape well? We can mix in a little bit of sulfur and heat that up, and that sulfur can react with some of those double bonds and cause cross-linking. And so that's vulcanized, because sulfur is one of the words, ancient words for sulfur is Vulcan. And vulcanized, adding sulfur into this polymer causes these cross-links and makes it more rigid and better at its shape. And holding its shape. Okay. Now we get into polysaccharides, and this is the most complex part of the poly. This is just barely scratching the surface. It's part of the ACS speaker tour. We heard a saccharide chemist come through, and he spent his whole career on carbohydrate chemistry because it's so complex. So let's look at some of these things. You've heard of these different monomers, glucose and fructose. We have different conformations. They can open the ring, they can close the ring. If you've had biochemistry, you've dealt with this quite a bit. You can make dimers, like disaccharides, trimers, and then polymers. And they have really a huge variety of different structures. So let's look at some of these different projections. We have Fischer projections, where they go from carbon 1 to 6, these are all hexoses, and you can look at the different ones that you have based on which side the OHs are on. When you make the ring formation, you can have this Haworth projection, or you can have some of these pseudo 3D projections. We don't have wedges and dashes, but by the angles you can tell that these here are equatorial OHs, because they're pointing out towards the outside. And that's one of the biggest differences in saccharide chemistry, is whether that OH is pointing out from the ring or pointing down or up. Okay, so this one over here, this one, all OHs are equatorial, and over here it's on an axial position. And that makes a huge difference. In fact, that can make the difference between your body being able to metabolize this or not. Okay. And so it can act as a sugar and a source of energy, or it can stay in the gut and just go out with the GI tract, go through the GI tract. This 1,4 glycosidic bond, we have the carbons numbered, and you can bond things at 1 and 4 and link those, and this is a 1,4' linkage, a glycosidic bond, using 2 equatorial OHs. Now, it's important to notice that this is what we call a condensation polymerization. I said there were different ways to polymerize. This one is a condensation reaction because it loses water. So, because this produces water, the ancient, like the first polymerizations, they saw moisture develop in the flask, and they thought that it was condensation. Well, it was actually from the reaction. So it's kind of a strange name for a polymerization, but you're pulling water out. So you have two OH groups come together. One oxygen takes two hydrogens with it, and you have this oxygen bridge left over. So you've reacted this OH with this one up here. You've lost water, and you've made this oxygen bridge between the 1 and the 4 carbon. And here are some structures of things that you've heard of. You might have heard of maltose, okay, from starch. So this, and then you might have heard of sucralose. It's an artificial sweetener. And so this, the body has a difficult time metabolizing this molecule, but yet the tongue, the receptors in the tongue, say it's sweet. In fact, it gives about 6,000 times the signal, so they say it's 6,000 times sweeter than normal sugar, and then your body doesn't metabolize it, so you don't have any calories. So that's the whole idea of an artificial sweetener. Tricks the tongue into thinking, hey, this is nice and sweet, I got a sugary substance, but the body doesn't get any energy from it. And so that's in this middle region of the polysaccharides. We also have DNA and proteins. We've covered DNA and proteins quite a bit in terms of other courses. And so that's why we're focusing mostly on starches and cellulose. Now, under those polysaccharides, we have starches, cellulose-related molecules, and chitin. So let's talk about those different kinds. Chitin is that polymeric substance on the exoskeleton of insects. Think about that rigid sort of body structure of beetles and roaches. It's kind of nasty to think about, but that's chitin. So it starts out with a polysaccharide, but then there's this extra glucosamine that's added on here. So this amine substance, sort of with an amine and an acetyl group on the end. This is 3 subunits of chitin. And you see this gives it quite a different structure. And now we have a different way to hydrogen bond. So at first we had OHs. OH groups can hydrogen bond to each other, create nice rigid polymeric structures. But now we even have more opportunities. We have an amide linkage. And so we have an NH and C and carbonyl that can also hydrogen bond. And those hydrogen bonds are going to be a little stronger. And so that's where you get that strength of chitin. So glucosamine, you take those over-the-counter supplements, you take glucosamine, you're taking that monomer that is basically insect skin. That's so nasty to think about. So. Starches, also using that 1,4 glycosidic bond, and they can be put together in many different ways. So you have amylopectin, which is insoluble, really long chains. It's characterized by many, many long chains, up to millions of glucose units. It can have 1,4 prime glycosidic bonds, and then also 1,6 prime. So it can branch off. And so the amount of branching is what really makes the difference between amylopectin and glycogen. This is useful for energy storage in the body. Why might you think that's the case? So you're putting these glucose units in a polymeric form. Okay, you can get them back too. So later on, if you want to harvest energy from this glycogen, you could pull those glucosidic groups off, those glucose groups off, and then use them for the body for energy. Which one of these has a faster reaction in terms of being able to pull those units off and put those units on? So amylopectin or glycogen? Let's count up. If we were going to do reaction rates, you've got to be able to get to the reactants, right? And so if you want to get these little units off of there, over here we have 1, 2, 3, 4, 5, 6, 7 end groups. And that's where it's going to react. So we have 7 opportunities to pull glucose off of this one. Look over here. Okay? So this is going to be much more efficient in terms of putting molecules on and getting molecules off. So the ratio of 1,4 and 1,6 linkages is important in terms of whether it's being used for energy storage or structure. These starches can be coiled up and made into structures. Most of the structures of our seeds and potatoes and those kinds of plant matters are mostly starch. And you can see how that structural material is pretty rigid. And it's the structures of these starches that give it its shape. So you think about a potato, the body of the potato is mostly starch. And so that's a huge example, one that you can touch and feel and have experience with in terms of its structure. Is pretty rigid, but not too rigid. Okay? It's held together mostly by hydrogen bonds. And then cellulose, quite a different structure, maybe even a little more rigid than starch, because you have these inter-ring hydrogen bonds. That beta-glycosidic linkage gives it a little bit more rigidity. Also makes it non-digestible. So, this is fiber in the diet, goes through and it can help your GI tract with its health. These cellulosic fibers coiled up and put into large structures are where we get the other complex plant structures, plant stems, and in the case of wood, the trunk and branches of the tree. This is a very complex structure. You have cellulose fibers and hemicellulose, and then you have a mixture of lignin and hemicellulose. And these lignins are not polymeric. These can still be pretty big molecules, but they're not necessarily polymeric. Now, of course, you have counterferryl alcohol. It has a double bond in it. It could polymerize. But most of the structure from stems and trunks of trees and branches and vines comes from the cellulosic fibers. These lignins are in there for various plant reasons, I'm sure, but we typically pull those out, and you can pull those out and still use the cellulose for structural usage. And that's where we get all of our papers and cardboard. We've squeezed out the lignins, and we actually use those in other chemical processes, and we've left behind the cellulose. And so we're using the structure of cellulose in wood. Now, in like timber that we use for framing our buildings, we have not squeezed all of the lignins out of those, but we've heated them up, and some of the volatiles have left. You have, for straightness, you can put that wood and you press it into form, and then you can heat it up in a kiln. You have kiln-dried wood. So you drive out essentially the lubricants, these lignins that lubricate those cellulosic fibers, and you fix that wood into a straight shape. And so most of our structural materials that we use have been kiln-dried and straightened, and so they maintain their shape. You wouldn't want to build your house out of really flexible green wood, and then when it dries out, it starts to bend and warp and twist. So it would be a mess. I did that once with a picnic table. You could not even eat on it. It just had really green wood, and then the boards all just warped, and the top of it looked like it was woven. And then if you go get, and it was sad too because that was treated wood. I thought, oh, this is going to be outside. I want to get treated wood, but that treated wood was really wet and green. So then I made it with kiln-dried building studs, and that stayed flat for the life of it. So we'll talk a little bit more about some of these complex fibers later on. But these lignins, when they're squeezed out, they're used, it's called tall oil. And they're still, even to today, when you think about how long we've been using wood, they're still, to this day, trying to find good uses for tall oil. So then the paper processing, they squeeze this this lignin's out. They have this oil left behind. It's a really dark black substance, fairly viscous liquid. You can see it's got aromatic carbons in it. It has some sulfurs and things. And they can burn it. And what's interesting is it's not a very good fuel, and it produces, again, if there's any natural occurring sulfur in there, it creates some SOXs, which are contributors to acid rain and so on. But because of the way the rules are written with the EPA, they actually get sort of some green benefit by burning tall oil because it's a bioproduct. So it's a bio-based product. They get green credit for burning it, but it burns pretty badly. It's not a great fuel. And so they need to rewrite that rule so that people aren't burning this really nasty tall oil. We got approached by a company in North Carolina to analyze the tall oil and to find its Hansen solubility parameters because they wanted to use it in terms of some industrial uses. And one of the things they needed to know is how it's going to react with other solvents. And so that was a pretty nice project. So again, they're still looking for uses of this tall oil because they produce quite a bit of it. If you imagine all the paper that we make in this country and around the world, we have this byproduct, these lignins. We can also take fibers and react them or treat them in many different ways. And one of the ways is to put clay in and around. I talked about adding carbon black to polymers to make them black and give them structure. Also, you can put in clay. Now, carbon black is flammable. It's carbon. But clay is not flammable. It's already oxidized. Okay? It's aluminum oxide and other different kinds of oxides. And so we can add in clay, and whenever that fiber is heated, the polymer will char, but it won't burn because the clay takes away the heat and protects this clothing. And so that's one way of fireproofing children's pajamas, bed sheets, any kind of bedding. Those have regulations on their fireproof nature. And so they will treat those fibers. So it's not just cotton fiber. It's cotton fiber with some sort of additives like clay to make them fireproof or fire resistant. They're not really fireproof. You can also take these fibers, like cotton fibers. They have all these OH groups on them. That's a great moiety for organic chemistry. Okay, CH2s are pretty non-reactive, pretty inert. If you give me a handle like an OH group, I can do something with that. And so you can react it with, like with a molecule that has a chlorine on it, and you can pull off hydrochloric acid and make that oxygen bond. And so this might be a trizene dye, and you come in and make this bond. So now there's a covalent bond. This is the cellulosic fiber, so cotton fiber. And now your dye is actually bonded to the fiber. So it's not just mixed in with the fiber, it's stuck to the fiber where it can be washed off. And this is how we make our color-fast fabrics, where the colors don't wash off. They don't fade. They'll still maybe fade over time as this bond is hydrolyzed again, so water can come in. And essentially, I mean, this is a simplified reaction, but if you make a bond here and a bond here, now you've put an OH on the dye, you put an OH on the fiber again, and it breaks the bond. And so that can happen over time, but that's a pretty slow reaction.
Is that why first time dye favored than just having 100% cotton?
Yes, they don't want any additives already on the cotton because then the molecule can't react with the cotton. Yeah. And now this is a strange reaction. So here we have the polymeric cellulose. So think cotton, ROH. Okay, so this is just the OH on the cotton. We activate it with base and carbon disulfide, and we make this cellulose xanthate. So we've put this strange molecule on here with these sulfurs, and it's actually extruded into solution. So this is soluble, this molecule, because it's an anion. And we can dissolve it in water, we can process it, we can extrude it into solution and react it with sulfuric acid and go back to the cellulose. So that's strange. We reacted our cellulose with CS2, and we pull the CS2 off, and we have our original product. Why go through all of this? What's the point of this reaction? Well, in order to spin this cotton fiber, into thread and so on, there's some old school techniques, okay, or there's modern techniques. And if we can react this and make it soluble in water, extrude it through these little, if you think of a sausage grinder, if you were, just imagine a sausage grinder, you're pushing the meat through these little screens, and it makes these little tiny tubular, or little tiny, I don't know what you call it, extruded strings of meat. It's the same kind of thing. Any extrusion process will do the same thing. And so we can take this cellulose, these long fibers that are not really very easy to work with because they're so coiled and twisted and so on. We can dissolve that in water and extrude it through these little screens and make nice, beautiful, straight fibers. And then we can pull the CS2 group off and get back to cellulose. And this is the difference. The top is natural cotton fibers, and the bottom is cellulose acetate fibers. This is rayon. And if we leave those acetate groups on, then we have rayon. If we take those groups off, we get back to cotton, then we can have nice straight cotton fibers if we use this process here. If we just take the OH groups and put the acetylated with, say, acetic anhydride, kind of like we did with morphine to make heroin, we acetylate it. So there's an OH group, we put a CH3 and carbonyl, we make an acetate ester, then we make heroin. In this case, we're making an acetate ester of the OH groups on cellulose. We're breaking up some of those hydrogen bonds and getting rid of that coily nature of the fabric, of the cotton. And so then we end up with these nice straight fibers. One problem with these fibers, and we did a feature at the beginning, and then they wanted to kind of get rid of this feature, was that the surfaces were really smooth. So the difference between these fibers up here, like the 100% cotton shirt and the rayon shirt, is the rayon shirt was shiny. Right? The smooth fibers, very, very shiny because they had a very smooth surface. And so they gave you more what we call specular reflection versus diffuse reflection. So just the reflectivity of the fiber was different because of the smooth surface. And that was cool, and it is cool. In some shirts, you want a shiny shirt, great, use rayon, okay? But if you don't want a shiny shirt, but you still want something that doesn't wrinkle, you want a little bit of rayon in that shirt, but you don't want it to be shiny, they'll add things to dull the surface. So those additives wash off over time, and so a rayon shirt will start out, if it's been treated so it's not shiny, and will get shinier as you wash it.
So what about shirts with brown shirts contain rayon?
Part of the work shirts?
The brown shirts.
Mm-hmm.
Do they contain rayon because then you keep those maybe dry shirts?
Oh, yeah. So I'm not exactly sure why the synthetic shirts or these semisynthetics, so this would be an example of a semisynthetic polymer, needs to be dry cleaned. Yeah. So that, as far as the dry cleaning is concerned, it has to do with shrinkage, and it may be the hydrogen bonding that the water does with the fibers. Okay. But as far as that, that's a good question because I haven't looked into that ever. Why you'd want to dry clean this shirt or that, not that one. Now, I do know that this is a semisynthetic fiber. Again, you can get it to go very straight as opposed to the coily and curly natural cotton. And so this will be also, you can spin thicker fibers here and get better shape memory. And so once again, shape memory shows up in fabrics, and that's your wrinkle susceptibility. So if it doesn't have good shape memory, then it can be wrinkled. It can sort of has a different level of shape memory. One leads to wrinkles, one does not. Also, the fibers sliding past each other. If they're able to slide past each other, then they don't wrinkle. Then we get into paper. We take those wood cellulosic fibers, squeeze out the lignins, and that's what this brown stock is, and the lignins, and those go into that tall oil. I don't know why it's called tall. And so we're left behind with those long cellulosic fibers that we can then press into shape. Sometimes they will process them violently to break the fibers down into shorter fibers to make the softer papers. And so inside those paper fibers, you have a lot of these domains of cellulose, and in between those domains of cellulose, they've been pressed into shape. Well, pressing them into shape does not fuse them. It creates lots of little pores where water can go. Because if you think about the surface of that cellulose, it has all of these exposed OH groups, and so paper is naturally, a cotton fabric is naturally water absorbing. So water can get in between those pressed layers. And so this is what you would see in terms of evidence. You would see, the cellulosic fibers, you'd see them pressed into a small space, and so on, and you would be able to tell from the random nature of the substance that it was a natural paper pressed together. They make woven fabric, wipes and things like cloth, and you would see the actual threads that were woven together. We have some examples of that in the lab. And then we get into hair. So over here on the left, we have some of the more complex shapes that we have for synthetic, like carpet fibers. This is the best we can do. I mean, we do pretty well, right? We can put our company logo, our S, in our fiber. Okay, so we can extrude letters into the body of a fiber. In a synthetic fiber, you might take a cross-section and you see an S looking at you and think, it's probably not a natural fiber. Okay. But hair, over here, this is what our hair follicle cells are able to do. Look at the complexity of hair compared to the complexity of something like these bicomponent fibers that we can make in our techniques. So extrusion techniques can produce this. Living organisms can produce this. So it's pretty amazing what we have in terms of the complexity of our fibers in natural hair. So here are some pictures of hair from that Olympus microscope site. And these are non-fiber. Let's look at hair in a second. And so we have the differences between acetate and silk. And some of these are under cross-polarization. Here are nylon fibers, flax and milkweed. And so let's go to this website and look at some of the micrographs of hair. It's pretty amazing. So you can go to Olympus microscope, or this is olympus-lifescience.com. And let's look at some of these digital image galleries. Under the polarized light, these are different crystal structures. I thought they had a hair library.
Here's an example of probably some of the most complex things that mankind has made. These are integrated circuits. Here's the Pentium processor. It couldn't be free. Let's look at that. Oh, come on, you gotta be bigger than that. Pretty complex. Trying to find my hair though. Because you can tell the difference between a beaver, a rat, a dog, a person. Yeah, let's see. On my hair. Let's see. So we can go back to the gallery now and see. Down feathers. Yeah. So again, you're going to be able to tell the difference between natural fibers and biopolymers, natural fibers, and sort of man-made synthetic polymers by the complexity of the micrographs. Yes.
So I know silk is bio. Is that as complex as hair?
It's going to be an extrusion, of the silkworm, and so it's going to be more like just a non-complex biopolymer, kind of like cotton would be, yeah. But it's just going to have a different, a different tertiary structure. It's going to either be, it's probably straighter than cotton because it's strung out to the spinnerets. So it's kind of like a natural extrusion, like spiderweb material as well. Again, it's not very coily. It's very straight because it's extruded to the spinnerets of the spider. It's always tricky to use some external source in your lecture because they change over time. So,
And we had Eric and there was a human
was there? Okay, thanks. Okay, and you can see the differences in the medulla here, this core. And so that's one of the main features that you can use to distinguish the different types of hair. Now, you wouldn't get this kind of complexity unless you got down into like a scanning electron microscope. So that would be a thin slice. You go down and look at this internal structure. What you're really going to see is the difference in the medulla. So that dark region in the human hair that we saw was different pigment deposits in the medulla. And that's really a major feature of the different colors of hair, is how much pigment is in the medulla. Any questions on the natural fibers? If not, we'll do a quick review the gunshot residue and arson stuff. So, which one do you want to do first, gunshot or arson?
Arson.
All right, let's go for it. Okay. Short code 50562. This will be tricky too because I don't know what y'all were taught. So this will be got a good chance to reteach some of the material that you may have missed. All right, let's go. What basic principle helps you identify the origin of almost any fire? It's a basic principle, that's the key. Yes, fire and heat rise. And so when you see that V mark on the wall, that's the heat, the fire rising, decomposing the wall, the paint, the drywall, and so you can look at that V pattern down to where the origin of the fire was most likely to occur. So procedural question. Does an arson investigator have to wait for a search warrant for gathering evidence? Correct, it's false. So they can go in and immediately investigate the arson. They need to do that. In fact, that's what they complain about with the fire department, staying too long and ruining their evidence. Okay, the NIJ report we talked about in my notes, so this is going to be difficult for you to answer, but just try to figure this one out. The NIJ report tries to connect the burn pattern to what? And so this the burn pattern on the floor. What are they really trying to figure out about that? So they see the burn pattern, what are they trying to determine? They want to know the amount of fuel spilled, right? Because if it's a little bit, someone knocked over a candle, okay, and there was a little bit of wax there and it burned, and it's going to be a small amount. But if it's a big, huge circle that burned in the middle of the living room, that was a substantial amount of fuel. That tends to tip you towards it being intentional. I mean, I guess you could be walking through your living room with a gallon of gas and a trip, okay, right, and then it catch on fire. Yeah, I don't know how it would catch on fire, but that's what they're looking for. Was this, like they were refilling a lighter and they dropped 3 ounces of lighter fluid, or was it a whole gallon of gasoline? The NIJ report concluded that the heat released by a spill on carpet was, compared to a fuel fire, was what? So there's a carpet burn, the fuel is burning inside the carpet. And this would be what's called a blind code. So if you haven't read the report, just try to think about the situation. Okay, it was about the same as. So a pool fire, if you take a gallon of gasoline, pour it in a bucket, and light it on fire, that's a pool fire. It's a pool of gasoline burning. And the heat released by a pool of gasoline is about the same amount of heat released from gasoline on carpet. So the carpet is making the gasoline burn as if it was just a pool of gasoline and giving off the heat that the pool of gasoline would give off. Now that's a nice conclusion from their report, because now they can see a pool of gasoline gives off this amount of heat, a pool of diesel, that amount of heat, and they can say that's the amount of heat that's going to be given off in carpet. It's not less or twice as much. I mean, you could think about it in many ways. You can say, well, maybe the carpet's contributing and making it hotter. Or maybe the carpet's taking away the heat and making it cooler. And their conclusion was, no, it was about the same. So it's as if the carpet's role is just to hold the gasoline, just like the pool. Okay, what is this called? You know this one? Yeah, it is like a, it's a Molotov cocktail. Yeah. Yeah. So it's not a drink. It's not one of the drinks down at the Jolly Fox. It's not a Red Bull either. Although that'd be a great name for Red Bull. So great. And then we'll do one on gun showers. There's the number. There we go, 345, 342. A friend of mine, she posted a picture on Facebook. I said, "Can I use this for my class?" Presence of GSR on a person's clothing indicates very good. You don't want to overclaim. You don't know that they fired it, but they were close enough to get the residue on them. What are these particles? So when you're looking at a micrograph of evidence and you see these particles, what is that? Tiny breakfast cereal. It's an electron micrograph. It's just not very filling. Yeah, so this is pollen. It's okay. The next question is related. Okay. How do you know these particles are not GSR, gunshot residue? They're about the same size, so it's not really. Yeah, right out of time. Because this is going to be the number one thing that confuses the GSR microscope, determination. Okay. If you look at that image, what would happen to that particle first when you started heating it up? Like when it starts to melt, what do you think is going to happen to that particle? The spikes. Those spikes tell you this particle has not been melted. Okay, and this is pollen. Those little spikes are to get that little ball to stick to stuff. Ideally to the other plant so it can fertilize and plants can reproduce. But also to stick in your nose for allergies like me. It's just like the stickiest little thing. But the point is, gunshot residue is melted. It's the metal parts of the primer, like lead stiffenate. It's the lead particles that come out, and the lead conglomerates and makes little melted particles. And they're about the same size as pollen, so that's why it's confusing in terms of size. But it's not confusing if you actually look at it and see this. Those little spikes tell you that's pollen. And this structure too, these aren't spikes, but those little ridges. And those ridges, the complex shape, tells you that that's been produced in that shape and it has not been exposed to high heat or anything like that. Or those structures would go away. Those would melt first. Yeah. They're very high energy. Any kind of point or ridge or edge is a high energy structure. So as soon as you give it enough heat for it to relax, it's going to go to a lower energy shape, and those ridges and spikes are going to go away. Okay, and this image is the different components of a cartridge. What is the primer in this image? Yay. Let's look at the others. So what is A? Cartridge casing. What is B? The bullet. What is this on the outside of the bullet? The jacket. So this is a hollow point. You see it's been hollowed out. This is a cross section of a bullet. It's been cut in half. This is a hollow point, and that's meant for the bullet to expand and distribute all of its kinetic energy in what it went into. Okay, like if you're hunting an animal, it goes into the animal and it distributes all of that energy and guaranteed to kill the animal, because that's the point of hunting the animal. It's not to harm it and wound it so that it crawls off and dies a painful death, but to kill it quickly. And same with anti-personnel bullets. That hollow point makes this thing a very devastating instrument because it expands. Okay, if you're just shooting target practice, you just get a full metal jacket that's got a flat top or maybe a pointed top, and it's got a metal jacket all the way around it. C is the powder, okay, and D is the primer. This bullet is going to have physical evidence on the outside as it goes through the chamber, and it's rifled, and so it's going to have marks that tell you what barrel it went through. The case is going to have expansion marks on it because when this explodes or burns inside, it expands the metal and sort of gets a print of the inside of the breech. It's going to have extractor marks where either if it's like a bolt action, you pull it back, there's an extractor mark. It's also going to have, if it's a semi-automatic, that's going to extract it as well. And so it might have an extractor mark on the side that, again, with microscopic comparison, you could say this cartridge was fired from the same weapon as the suspect. And then the primer in the end is going to have the firing pin mark. And the firing pins, again, can be different in terms of oblong, maybe they have a defect, and you can tell that was the same firing pin that fired this primer and that primer. So you can use microscopic comparisons. Those are called pattern evidence. It's really not part of this course, but it's physical evidence, patterns in all of these figures. And then the chemical composition of the powder. You can trace it back to the manufacturer and probably even the lot number. So you can do chemical analysis on the trace amounts of impurities, and you can get, this is a Winchester Blue Dot powder made either one of these lots. You can maybe specifically work it down. They were talking about putting tracers in the powder so that you could definitely trace it down to what lot it was and what manufacturer it was. So those are our review cahoots, and then next time we'll do the synthetic fibers.